Hello, my name's Relevant. Welcome to the show. This is Do All the Things. And on today's episode, more noisemakers, specifically a bell ringer. Ah, yes, a bell ringer. What's the point of the bell ringer? Very simple circuit, but I've got it all timed up here. And any second now, we're gonna see. Good timing. And then there's gonna be a long pause before it fires again. Bit of a duty cycle, ring, longer pause than ring, then ring. And what is the point of this? Well, in a previous episode, I built an alarm for this one effluent pump that I have out of parts that I scrapped out of a smoke detector. Now, there's no scrap parts here other than this thing. This thing came out of an old school PA, like literally an old PA system that was in a school. At least I think it was in a school. It looked like the one that was in my school as a kid. I'm not sure what purpose this bell served on that, but it's handy for my application here today. And one of the reasons why I want to build this driver circuit for it is because these things had a very mechanical way of operating. You basically, shock the voltage onto there. That caused the magnets to jump and hit the bell, but that would open that contact, demagnetizing it. It would fall back, but then that would close the contact, remagnetize it, and so on and so on. Thing is, the contacts are a bit, they're getting a little long in the tooth there. And I found the bell, it ran rough every now and then when I tested it, because I did have this with just a wall wart plugged into a float switch for that pump. And anytime I tested it, it had a rough sound. Sometimes the mechanics just kind of locked up in weird ways and it would just kind of make this. That's no good. I want something a little bit more reliable. And it occurred to me, I can use some of my logic circuit buddies here to control on this bell. So we start off with this very simple circuit. Our wall wart, 6 volt DC, 600 milliamps, has enough chooch to run this. Now we have a bit of a circumstance where that is under load, that 6 volts. A rough 6 volt power supply that doesn't have regulation on it could put up anywhere up to 8.4 volts DC without a load. And logic circuits aren't an appropriate load. So we had to use a little bit of regulation right here. Good old fashioned 5.1 Zener, 22 ohms of dropping got me where I needed to be. And so we have right here a good old fashioned relaxed oscillator with a duty cycle. We got 1 meg of main feedback and 220K of the duty cycle feedback, and a 473 capacitor pulls it all together. I get roughly 30 hertz out of it. As the bell turns on and off, it causes voltage dips in the circuit, which makes the oscillator change a bit, but for the most part the circuit's stable, so it's not a problem. Now this is going to give us a waveform that looks roughly like this. We're batting 35 hertz right now, just raw out of it, with a duty cycle 15%. Now one of the reasons why I did this is because this is, how do I put it? It's a bipolar magnet assembly. The way it's wound, it doesn't matter what polarity you give it, it's just going to pull the hammer. So we don't have the ability to AC modulate it, going back and forth, pushing and pulling the hammer for a really potent strike. So basically these little pips right here, these 15% pips that are dictated by that 220K resistor, that is the strike. I found if I use a 50% duty cycle, it's kind of holding it on there too long. If I went with anything less than that, it didn't hit well enough. Anything more, it was, holding too long. 15% seemed to be the sweet spot. If I actually engage on this bell, we might see that waveform change. Oh, it's peaking out to 40 hertz. Oh well. Sadly, that oscilloscope does not have screen capture, so I'm not sure the best way to film it yet, and I need my better cameras for other things. So how do we turn this little signal into a nice voltage current to drive that? Well, we're using a little something called a MOSFET driver, specifically an IX-DD604PI. This little puppy right here by a company In Excess. I keep thinking of the band In Excess. IX, well, let's look at the figure. IXYS. I'm a fan of their LL8108 solid state relays, and now I'm a fan of their MOSFET drivers. So we're using a pupper right here, DD. It has 2 circuits, non-inverting, so what you put in is what you get out of them, but they have an enable pin. Now we don't need any inversions because we're not trying to do an AC waveform. We're just trying to turn this pupper on and off. Now this guy is a 4 amp part that, according to the data sheet, could do a 1 amp sustain. But 4 amps, well, we're not really sustaining the current, we're modulating it, right? I'm running these 2 guys in parallel as per the schematic here, in, out, out to the bell. We have this capacitor here right close attached to it because like the way this bursts current, that stabilizes situations. And this guy's basically taking the signal the oscillator's putting out and then hammering the bell with it. And the thing is, with the current capability it has, we don't actually need to drive a MOSFET. We could do this directly. Now, I did some experiments. If I try to use a MOSFET instead of this, the logic doesn't quite have enough chooch to drive it. I would need a MOSFET driver anyway. So we just get a higher current one, chuck her in there, and she's good. Now that would just ring our bell. That's represented over here. That's not exactly the schematic symbol you would use for that, but it was close enough. Then of course I have a freewheel diode for when that disengages. Theoretically, because of how a MOSFET driver works, it has its own freewheeling action in, because it will go connect to your high bus when it wants to drive the bell, but then on the inversion of the waveform, it's going to connect to negative, which would be an automatic freewheel. That only helps us when it's continuously oscillating. When it hits the actual on-off duty cycle, well, that's where the freewheel is going to come in. And that's dictated right here by the warbler, as I call it. Again, we have a relaxed oscillator with a main feedback of 1.82 megs and a return feedback of 1.5, 22U because we're going a bit slower, and that connects to the enable pin. It's one of the reasons why I chose this specific part, because that enable pin makes it really easy to turn that signal on and off. Basically, this guy enables high, disables low. When you disable it low, it goes high Z, cuts the power to the bell altogether, which is kind of important because if we just hooked it up to that MOSFET driver, it would put out some sort of signal based on the input signal. Now, mind you, in theory, when the oscillator goes low, it would pull the output low, which would do nothing. So we could probably get away with it, but this was the most convenient way to connect that up without any trickery. Now, if you don't know how a relaxed oscillator works, we have a Schmitt channel inverter. When the voltage input hits a certain threshold, the inverter switches instantly, no lag time. So the Schmitt inverter puts out an active signal. Now, let's say it puts out a low signal. It's putting out negative. It's gonna go over here, discharge that capacitor, charge that capacitor, something to that effect. But because that capacitor needs to be charged or discharged, it's going to take time to do that. Once that happens and this signal goes low, then the output switches high, and then that high will come through here and slowly charge that capacitor. We could create an oscillator and set the time of it by a combination of the resistor and capacitor. And what we do with this duty cycle pupper right here is when it goes high, it can pass through this diode to a different impedance, and that's what gives us the different duty cycle. That's why up here on the main oscillator, we're getting 15%, because the cycle from high to low is a lot faster than the cycle from low to high. All in all, it's a pretty simple circuit in its functionality. Initially, I was going to have a more complicated warbler circuit where it kind of goes like dring, 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 long pause, dring, dring, dring. But I opted out of it because I thought it was fine the way it was. So that third circuit, well, I wanted to add a little bit of light, a little bit of flash, you know, a little bit of smash, a little bit of wow factor. And that's done with just basically this last oscillator connected to an NPN transistor. In this case, it's a 2N4401, and then that just drives a LED. Now, we needed to use something in the general N channel because we have a regulated high. The high signal that this puts out is going to be the same voltage as our regulation circuit. So I tested it with a P channel, and because the potential voltage going to the transistor coming off the main rail is higher than the potential voltage coming from the signal, it didn't work properly. It didn't open and close all the way. But these guys are directly connected to ground, giving a full ground signal, turning this off, and it just worked better with NPN. So for the logic component, I'm using a little 3G Schmitt inverter, specifically a Toshiba TC7W14FU. and then LF is the size form factor. They're not in stock, which is the reason why this is a one-off. I might not be buying more. I was looking for a 74HC 3G14, but I couldn't find one at the time, so I decided to give this a try. It fits all the general specifications that I need, and unfortunately, now that I designed this circuit for this component, I since acquired a 74AHC 3G14, popped it in there, and the circuit didn't work right. So it would probably need a little bit of tuning and calibration to work with a different inverter. I'm just gonna stick with this guy right here, get it done. If you are interested in this part, it comes in 2 different sizes, and if you want to be able to solder it onto this adapter, you got to get the LF, because that's our TSSOP8. The LAD I'm using is a Cree. There's the part number. It was one of the most powerful ones I could get with certain other specifications that I liked in a color temperature that I liked. I did a trainer mod where I installed an LED instead of the pilot light, and it was a warm white. I didn't like how the warm white didn't penetrate lenses very well. It was okay with red, sucked with green. I decided to try something different. This 6500K has no problem punching through, and she's pretty bright. Oh yeah, that's going right through that lens. So, what's the story? What am I doing with this? Well, I'm building on it. I'm going to officiate this project today, and unlike other projects, I'm pretty much going to start with fabrications. I spent an hour in traffic just to go pick this up quick in a hurry today. This is getting installed into a wall here in the house because it's going to live there. And I'm going to be using a rework box, and I'm going to be installing this circuit onto the other side of this stainless steel cover. So I'm going to start by getting this cover ready. And the plan is we're going to have a light right in the center. This is actually a Russian surplus pilot light assembly. It's got the screw for the screw bulb, but I don't need a screw bulb. I'm using an LED, and I just want this to be a kind of a shroud. So I'm actually gutting out the bulb components, probably repurpose them elsewhere. But you know, bulbs are kind of passe now, especially for indicator light purposes. This LED, conveniently, the layout of this thing, I can just drop the LED. It sits nice in that little center slot at the bottom, and then the cutout holes at the bottom are convenient to pass the LED leads, which is actually a good thing, because one of the flaws of this is because it seals the bulb in there, it gets really hot. So I gotta figure on where roughly center is on this pupper. It's 7 centimeters edge to edge. So we're gonna be doing 3.5 by 11.5 centimeters. That would be 5 3/4 right here. That's center. That's where we want our LED bulb. Now for the mounting holes, we got to get a perf board on this pupper. And here's the layout that I came up with. It's not the most elegant. It got tricky. I feel like I don't like working with a triple inverter. There's a reason why I don't use 6-channel hex inverters, because they're a pain in the ass when you're trying to make a tiny compact circuit. To have that big chip and half of it's useless, and you have to ground that out, and there's not room to work around. Here, especially with the one inverter pointing the other way, it got a little bit tricky. And I kind of had to work around the positioning of this LED too. I wanted it to be exactly dead center. So that made it tricky, but I came up with something, and it's not completely a mess. Only one overland connection I needed. But we're gonna have the kep nuts on the very edge of the board. Fortunately, this right here is part of a ground bus, so it's okay if the kep nut touches those pads. This is a ground bus too, but you know, we don't want ground loops. Even if it doesn't matter in a circuit, it's still bad form. Now those holes for the kep nuts are going right on the edge here somewhere. Close enough. I'm actually putting them just a touch farther out than they would be specified in the design. And I messed up the centering of that one, but it'll be fine. Actually, we might not actually use kep nuts on this. We have ourselves, oh yeah, no, we're not using kep nuts. We're gonna be using screws because we're mounting this pupper a whole inch off so that this LED assembly clears, and then the leads are gonna go into the center. Either way, let's get these holes drilled. Getting a bit blunt there, bud. Now I just need a way to judge center here. It's actually quite easy. Let's just go over this dot. Dun, 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 dun. That should center things up right there. That will be where we drill our screw holes. Pew, pew. All right. Let's bust out Mr. Pressy Boy. Quite conveniently, this stainless cover has like a plastic protective sheet on it, so we can work on it without chattering up the finish. Now we need a hole on the center of this thing to fit this guy through. What size? Have I drilled a hole for one of these yet? Of course, measuring device. It's about 50.78. That's 16 millimeters. I don't know that I have a chassis punch that small. Not 16 mil. Holy crap, I do have a 16 mil chassis punch. Oh, this is gonna be a clean hole, bud. Problem is, we need to get a hole big enough to get the shaft through to begin with anyway, so maybe it's redundant. Well, let's see. Let's start by sticking a Coney boy in here. Okay, this one's a bit tricky. This is a bit that can jam up and slice my hands open, so. Ha, close enough. You know, we could just keep going with the little cone spinner here, but I don't get to use these tools that often, and they make clean holes. The idea is we take an adapter dealer. Now we need grease. Basically where the shaft is interfacing here, we do not want to run that dry. Yes, it can spin nicely. Then put that pupper through there. Put this pupper through there. It's gonna lock up. And it's just a case of putting some spinny torque into it. Holding on to the workpiece is the hardest part here. Oh, I'm gonna need the glove. Oh, I'm getting grease all over. Gooey. All right, let's ungrip this puppet. Oh yeah. You know, sometimes when you go looking for chassis punches, they don't have manual ones like this. There's like some hydraulic assembly that goes with it. See, it's just cutting through. Right, I think we're through. You know we're through, and we can waggle this out. I need just a touch more. Yep. You don't want to like, there's a point where once it gets through, if you keep torquing it, you're going to damage the cutting heads. But it should, yeah. Perfect holes, bud. Perfect holes. Ha, how lucky are we when we find a perfect hole. Bonus points feel like Mexican. Bonus points feel like Mexican because you end up with a kind of taco after. Oh, that's the gist of fabrication. We can move on to the electricals, which I'm not going to film because I filmed perf boarding already. So let us skip to assembly. Except first, don't forget to chamfer and deburr. Just check the fit here real quick. Oh yeah, those holes are going to line up perfect. That guy sits right in there. Ooh, we have a little notch. Just an alignment thing. We're gonna need to notch this. Got a square file on this maybe. There's a reason why stainless steel stuff costs more money. It's not as easy to work with. We should get a consultant in here. Oh, this will be much easier. Oh no, we need more notch than that, bud. Okay, good. Little curveball. We got a notch in there now. Line up with the thing on here. Oh, that's gonna make for a nice anti-rotational fit though. So it's a win-win. And they give you these. Oh yeah, it's much easier to mount these when they don't rotate. Haha, yes. Okay, now let's clean up this mess. All right, after a couple hours of it's done. Oh, how do you like that? The only thing that's not there is the LED that gets mounted after we fit the board. And I decided to socket the MOSFET driver because, well, I don't know that they're exactly intended to be used the way I'm going to be using it. So a little bit of redundancy. There was one mistake in my layout, and that's this guy right here was connected to positive when it should have been connected to negative on this negative bus right here. That's our power in. The bell connects there and around there. I've already got some lead wires attached. They screw on and off to the bell, so they're easy enough to disconnect, and it's going to get cut to length once I get the bell hard mounted. I scrapped out of an old power supply the fan power connector, and that's going to be how we attach power to the board. Oh, there's a free radical that didn't get snipped, bud. We need to take ends from this power supply and attach them to the ends of this wire connector. And before we do that, I need to plug this in and double check my polarity. Wouldn't that be awful to get it backwards after all this work? All right, we got a wire with a stripe here. Sometimes that's negative. This is not that time. Got negative 8.6. Remember what I was telling you about voltages being higher than advertised? That's why we have the regulation on the logic. Okay, so positive is the one with the stripe. All right, a little bit of a bottleneck. These wires are a bit smaller, but it should be okay. All sorts of mixed bags here. Let's get some heat shrink ready. Sproing. Hot bud, spicy, splicey. Good, this wire all tacks up well. Hit it with the heat. Oh, let's double seal it all in with one big piece. Bring the heat. Now the bell is still, oh boy. hooked up to the other side of this wire that I've tacked on here. It's just a case. Oh, what's this? Oh, there's a line here I forgot to tack onto the ground bus, bud. Okay. We'll make quick work of that. It's supposed to go into this hole here. Oh boy. Now we have a situation where this is going to be crossing. There's an intersection here. Oh, by the way, remember, if you're working with the kind of IC adapter that I have, it's double-sided. Make sure you Captain tape the bottom side of it so it doesn't short out when it touches the board. That intersection, because it's a double-sided board, we need to clear the pad off of it. There. Now it's won't short out. Basically, without this wire in place, our blinker wouldn't oscillate. Our blinker wouldn't blink. Fortunately, it's nothing that can't be corrected in post. Just a little bit of sloppy. A lot of attention to detail in perf boarding. I quite enjoy puzzle and challenge of it. Now, assuming, yeah, we all clear. So, if I put in the crystals, specifically Mr. MOSFET driver, and now I attach power, that bell should start ringing. It should stop ringing too. The first bang is rather long, and if I touch the LED to these two stray wires, yeah, it's blinking. Okay, that's enough. Let's get this ensembled. So what do we have here? So we got a 1-inch spacer. It's time to finally peel. Are you ready for the satisfying peel? Oh yeah, here we go, bud. Are you ready? Oh yeah. Oh, those sections there are a bit humpy, bud. Well, wonder if they'll flatten out with a bit of screwing. Alright, just torque her tight, bud. It looks like it'll be fine. These are standoffs, 632 standoffs by 1/4 inch, I do believe is the OD. I get these from Mauser. Digi-Key might have them too. I love hardware like this. It makes doing these projects so easy. Now, line up that notch. That notch has a rough edge. Gotta do a quick little bit of fish beer back. That's better, except I'm getting fingerprints all over this guy already. Gonna look used and abused before it even gets installed. All right, light holder, you get on there. How tight does this thing go on? And what size is it? Not that size. Yeah, I'm not gonna go bother digging out another wrench. Just snug her. She's plastic, bud. Okay, so this will just screw onto here now, some way, somehow. You know what's perfect for this kind of thing? Computer screws. Course thread computer screws are 632. And I got these ones with the Torx head that come out of old compact machines. This is a perfect place to use them. You know, they got the serrations on the bottom that are gonna, you know, grip a little bit. But we're also using up these guys we don't want to use in our actual computer builds because we don't want to have to bust out a different screwdriver just because, like, we're changing a hard drive or something. But here, it's set it and forget it. We're putting it together and that's it. So tighten that, not too tight, that would be cruel. This is the wrong size screwdriver. Fortunately, they support a little bit of slot action. I think I want to blast a bit of Loctite on that guy. Always get the proper screwdriver, because they have some looseness to them. We don't want this coming out. Bloop, bloop. Oh, hey, Loctite's not conductive, right? All right, got all over myself too. Where's a piece of scrap paper telling you? Oh, the fingerprints are real. So's the weird feeling of Loctite on your hands. So now we have to get Monsieur LED into place. Where did I put it? Right here. I'm gonna have to order more of these. I like them. So the top is positive. Yes. And that's gonna be the long lead. So we gotta kind of drop her in like this. And we have to guide those wires into the right hills, which should not be hard. Oh, there we go. I'll make sure it's seated nice in there. Yeah. It's probably gonna want to fall out on me. As much as we like that game, it's inconvenient when you're trying to seat an LED. Let's just stuff some foam in there, bud. Okay, one last connection to make here. Wonder if we can gently get the outside of that holder in the soft jaw vise. Okay, it's not a good grip, but it should be good enough. Now we just have to connect the LED via the overland connections that I've prepared. Or you know what, I'm gonna pull slack upwards, because if we ever have to service this, we need to be able to get that LED out. That's really all we need right there. Now with this resistor, it doesn't go through. I just gotta surface tack it down right here. It doesn't go anywhere. Pretty sure there's nothing passing beneath there. Not according to the schematic, that's the landing pad. And then we can just bring its wire around and get it gently wrapped, which will probably hover a bit. So we'll tack down the LED here. Me trying to make everything nice all the time. Oh, okay, we got it. Just tighten it up, snug it, snug it, snug it, nug it. That's a little loose, but it'll be fine. Again, it'll make it easy to service this if we have to pull that LED ever. All right, Yeah, that LED pretty much stayed in place. Looks like it tilted a bit though. Yeah, nice, look at that. Let's stick the lens on. So that's what the assembly that's gonna be sticking out of our wall's gonna look like. So now if I plug the power in again, we should get sound and lighting. Avert your ears. I gotta disconnect the bell. Just for the time being. Yeah, look at that. I guess we could have made that pupper blink a bit faster, but that'll be good enough, you know? You're not gonna miss that. And in theory, if something goes wrong with the bell, you'll still see that. This is going on the field bed pump, which actually takes a while to fill up, especially one guy living alone. And even when it does, you have some time, you know? Unless you're draining water, it doesn't fill up anymore. So if you catch the alarm, you can mute it and deal with it in the morning if it's that kind of situation. I like that. Just that nice slow blink telling you something's wrong, bud. Now to mount that on the wall, we have a rework box. I got one with the punch out. We don't need the extra crap because it's not going to be dealing AC. In fact, this is a bit overkill. Like we totally could have used like a low voltage bracket, but I just like that mechanical enclosureness. Get rid of the superfluous attachments. So the plan is, we punch this pupper out here, and I get one of those cheap plastic connectors. Ones that I don't actually take seriously. I don't like the idea of them for Nomex. I guess they're okay, but I don't know. It's advancements in technology that you know is done for making things cheaper and quicker. But I guess if it passed code, ding. I don't seem to have any in stock. I thought I did, but I can't find one. I'm gonna have to run all the way back out to the electrical supply store for one 25-cent piece. Nice. And the idea is making sure that these ends do not short out. We'll tie a strange knot here. You know what? I should have put fusing or something in this. Completely didn't think about that. I don't know what's gonna happen if the bell shorts out. Might fry this thing. Is it too late to put a fuse just on the bell? It would connect right here. I suppose I could, and maybe I'll do that off camera. But let's see if all this is gonna fit in this box proper. Should. This is a deep arse box. Oh, yeah. I just have to get this mounted onto the wall. And then we're done. I don't expect that bell should short out unless the wire comes loose. You know what it'll probably do? It'll probably burn out this pupper here. And then, well, that's replaceable. So it'll be a $2.50 fuse. But anyway, there it is. This ensemble is done. Ringer and a blinker. Now all I have to do is install it, which might be subject to another video because it's kind of irrelevant. It's not technical. I'll make a video about it, so stay tuned and you can see me actually install it. I just basically have to cut a hole in the drywall. I can get to the wall behind because it's like a utility crawl space underneath where the actual stuff is located. So it's a piece of cake. You just cut a hole in the wall, pop that in there, attach the wire to the bell, screw it down, plug that thing into the float switch for the pump, and we're done. That said, I hope you enjoyed this. Stay tuned for more. Okay then.